All right, let's talk about chirality. If you're watching this lecture at home, you're going to want to, or in the classroom, um, ideally you do this with models. So either borrow some models from class and bring them back when you're done, or do this in the classroom where you can build some models of molecules. This is a topic where really the spatial reasoning gets difficult, and it's important to have actual physical things to hold in your hand and look at from different angles, etc. So, chirality is this fancy word that's also called handedness sometimes. So, chirality comes from, I believe, the Greek root for hand. Anyone speak Greek? Handedness. So chirality is this property that certain objects have. And it's the fact that you can have an object that is not equivalent to its mirror image, or not identical to its mirror image. Another word we use sometimes is superimposable. We say two things that are identical to each other are superimposable. You could put the two things right on top of each other and line up every part of them in exactly the same way. So when we say not identical, you'll also hear the term not superimposable. On its mirror image. Can anyone think of objects that you might be familiar with that might exhibit that property? Oh, hands. Yeah. Hands, feet. Your left hand and your right hand, while they are mirror images of each other, they are not identical to each other. You cannot superimpose one on the other and line all the parts up. You know, if you try and line up your one thumb with your other thumb, you'll notice your two palms have to come together, and your two hands are facing the opposite way. If you then try and line up the back of one hand with the front of the other, your thumbs are on opposite sides. So hands are the perfect example. Feet also. So your feet, your left foot and your right foot, they are mirror images, but they are not identical. One way to kind of prove to yourself that they're not identical is to imagine you saw a picture of someone's left hand or right hand. Could you tell that it was a left hand or a right hand? Yeah, you can tell them apart because they're not identical. But if asked to explain how they're not identical, you need to use directions, right, in order to explain how they're not identical. So you could say, well, this is a right hand because if you look at it with the back of the hand facing you, the thumb is on the left side and the pinky's on the right side. But the explanation of how they're different has to involve directions. Also, shoes are chiral. A left shoe and a right shoe. They're not identical, but they are mirror images of each other. Most winter gloves are chiral. Some other things that are chiral, almost all of the structural molecules that you're made of. Not counting the water. Water is not chiral. But most of the organic molecules that you are made of are chiral. And it turns out that chirality has a huge effect. In a lot of cases, one mirror image of a molecule has completely different properties in a chemical environment to the other mirror image of the molecule. And so we're going to need a way to keep track of this in molecules and identify when it's an issue. Question. The question is, do we ever care about chirality in inorganic molecules? And the answer is absolutely yes. But not in this course, because we won't deal with a lot of inorganic molecules. But if you ever take an inorganic course and you deal with transition metal complexes, definitely there can be chiral transition metal complexes, and then you get into the combination of like organometallic chemistry, and there are a lot of chiral like catalysts for reactions that you can make, with metal atoms with chiral organic parts coming off of them and stuff. So definitely chirality applies beyond organic chemistry, but you don't run into it at the like basic intro level of like general chemistry. You run into it more at a higher level of inorganic chemistry. But definitely this spatial reasoning, if you take an inorganic chemistry class someday, you will deal with a lot of the spatial reasoning, and you'll assign what we call symmetry point groups to different molecules. And so, yeah, definitely that this comes into play in the inorganic context as well. So how does chirality arise in organic molecules? While there are some other ways for it to arise, the main way that we end up with chiral molecules is through what we call asymmetric carbons. So an asymmetric carbon atom is a carbon bonded to, oh, actually, I left the AKA there because sometimes we call them asymmetric carbons, sometimes we call them chiral centers. Sometimes we just call them stereocenters, although that's a more general term. But an asymmetric carbon or a chiral center is going to be a carbon atom bonded to 4 different groups. And I want to emphasize groups there, because if it's bonded to a methyl group and an ethyl group, both of those, they would be bonded to a carbon atom. So it's not that it has to be bonded to 4 different kinds of atoms. It has to be bonded to 4 different groups. So in that case, a methyl group and an ethyl group counts differently. So you have, classic example would be carbon bonded to, say, hydrogen, bonded to bromine, a chlorine, and a fluorine. Or you could have carbon bonded to a methyl group, an ethyl group, a hydrogen, and an OH. And I do want to point these abbreviations out again because some people are still confused about them. Methyl is CH3. We abbreviate it as ME, ethyl, ET. Lots of organic chemistry is just about getting to know the abbreviations. Abbreviations are an important part of what we do. Because if we didn't use them, we'd spend forever drawing things. So asymmetric carbons are what give rise to chirality in organic molecules. So most of what we're going to do is going to be focused on identifying asymmetric carbons and then being able to classify them in some way. Because if we want to keep track of which mirror image we have, we need a system for that. Just like we needed a system to say whether a double bond had E or Z configuration. And we needed a system to name molecules. This is another case where we need a system. Luckily, I think this is the last naming convention system that we are going to cover. So, if you get bored by that tedium of, just following a set of rules, following an algorithm, this is the last time we have to do it. So, I'd like you to take a carbon atom, take a model of a carbon atom, and bond it to 4 different groups. You could use 4 different colors to represent those 4 different groups. And take a separate carbon atom and bond it to the same 4 colors. So you're making two models, 2 separate models. One with a carbon atom in the middle, bonded to 4 different things. Make sure it's a tetrahedral atom. And then take a second carbon atom, bond it to the same 4 different things. But don't bond the 2 things together. So I have an example in my hand. Maybe I'll try and do a little video and also see if my recording system has... Alright, so what I have in my hand is an example of the models I want you to build. I have a black atom in the middle that I'm using to represent carbon. I've put 4 bonds around it. And I've bonded to 4 different colors. White, yellow, red, and blue. Doesn't really matter what 4 colors you choose. And then I made a second one. And you're going to take the 2 models that you've built, and what I want you to do is try and superimpose them. So try and take the 2 and line up all the 4 outside atoms so that they're all the same. So I'm going to start by taking my blue and yellow atoms and lining them up. And if I bring the 2 models together, I ask myself, okay, do all 4 atoms line up when I line up the blue and the yellow ones? Did they all 4 line up? No, they don't. The red and the white don't. I could say, all right, well, let me line up the red and the white. So I flip it around and line up the red and the white, and then put them together, and the yellow and the blue don't line up now. So I'm not going to be able to line these 2 up. What I have are 2 chiral molecules that are mirror images of each other, but they're not identical. Now, if you found that you could superimpose the 2 that you built, what I want you to do is take one of them and switch any 2 of the groups. If I take mine and switch 2 groups, then what I find is now they are superimposable. I can line all 4 up now. If yours could line up before and you switch 2 groups, now they won't line up. So what I have, I'm going to go back to my 2 mirror images. So that's essentially our model of chiral molecule. It has a mirror image that is not identical to it. So once you've played around with the models for a little bit, and you've got this basic idea of what chirality is in a molecule, and how it arises from having a carbon atom bonded to 4 groups, we're going to need a way to keep track of these asymmetric carbon atoms. Sometimes a molecule will have only 1. Sometimes there'll be lots of them. So when we want to keep track of asymmetric carbons, we need a system. And the system we've come up with is to give them a designation, just like when we had double bonds, where we could have EZ isomers. We need a system to keep track of asymmetric carbons. So we can designate each asymmetric carbon as having R or S stereochemistry. This term stereochemistry is what we use to refer to differences in isomers based on the geometric arrangement of groups. So stereochemistry is whenever two molecules are isomers of each other, even though they're connected all the same. So EZ isomers are stereoisomers of each other because they differ only in the arrangement of groups in space, not in the connectivity, not in the way atoms are connected to each other. So stereochemistry has to do with differences between molecules based on arrangement of groups in space. Not differences in connectivity. And so we have this system, just like for double bonds, we could say it was E versus Z. For asymmetric carbons, we call them R or S. If you're interested, this is where the language actually doesn't make sense because these refer to Latin terms, and S stands for sinister or left. R stands for rectus, which actually means right, but not the direction right. I think it comes from the root for the direction right, meaning like just. So it was a situation where I think they screwed up their derivation of the letters. So any Latin scholars in the room? Yeah, so German, the R would make sense. Recht would be right, but left in German doesn't start with S, right? So whatever it is, the R and the S, who knows who came up with those two letters? Don't try and make sense of them. They're just the letters someone chose. Kind of like our atomic orbitals are S, P, D, and F because someone chose those letters. So we have a system. And the system is as follows, all right? If you're watching at home, you might want to pause to copy this down. If you're in the room, I don't know that I'm going to wait for you to copy all this down just because it'll take too long. So let's just read it together. First, you have to look at all four groups and assign priority to each group, all right? Since you've already learned how to do EZ isomerism, there we learned the priority rules. The priority rules here are the same as they were for EZ. That system is called the Cahn-Ingold-Prelog system. If you ever hear that, it's named after three people, Cahn, Ingold, and Prelog, I guess. So we have the priority system. There's a reminder of that on the next slide. So you assign priority to all four groups. So you would hold your atom, you could take your model in your hand and look at the four colors and decide, okay, I'm going to say on my model, yellow is priority 1, and red is priority 2, and blue is priority 3, and white is priority 4. So the official system has to do with holding a model of the molecule and pointing group 4 away from you. If you watch an online lecture about this, that's what it'll tell you to do. If you if you read the official system, that's what it'll tell you to do. I'm going to tell you to do it a little bit differently. So this is going to be slightly different from what the official system would say, but it'll work. And you don't have to build a model of every molecule to do it. You can do it on paper. So what I'd say is make sure that the lowest priority group is either going into the page, which would mean on a dashed bond, or coming out of the page on a wedged bond. That's pretty convenient because 99% of the time that'll be the case. Most of the time, what do you think the lowest priority group bonded to an asymmetric carbon will be? Hydrogen. And it just so happens that we very rarely actually draw hydrogen in the plane of the page in any of our molecules. So if you go back and look at all the molecules we've drawn, very rarely is a hydrogen in the plane of the page on an asymmetric carbon. So this works most of the time. The hydrogen is either going to be a wedge or a dash. Remember, hydrogen might be an implied atom. So if there's a wedge showing and no dash showing, then you assume that the hydrogen is on the dash bond. Once you've done that, take your finger and trace on the page from priority 1 to 2 to 3. All right? So you take your finger and just trace on the page. You're either going to be going clockwise or counterclockwise. The RS designation is different depending on whether group number 4 is on a wedge bond or a dash bond. So if number 4 is on a dash bond, meaning going into the page, in that case, clockwise equals R and counterclockwise is S. If number 4 is coming out of the page, then clockwise is S and counterclockwise is R. All right. So let's apply it. Oh, I forgot to put in the slide with a reminder of how to assign priority. I will go back and add that in. But let's practice. All right. So the two molecules I have drawn on this page. Each one has one asymmetric carbon. When you just glance at a molecule, what's the quickest way to tell when there is probably an asymmetric carbon? All right. Well, okay. But what's a vision? So the response was, if there's a carbon with 4 different groups. But what visually about the molecule will kind of make the asymmetric carbons jump out at you? It's got to have a tetrahedral structure drawn. It's got to have a wedge and a dash somewhere. If there's no wedges and dashes shown, then either that's not an asymmetric carbon, or whoever drew the molecule is not indicating the stereochemistry there. If there's no wedges and dashes shown, you can't tell whether something is R or S, because it hasn't been represented as a tetrahedron. But for these two examples, we see each one has one molecule that's clearly represented as a tetrahedron. Now, occasionally something won't be an asymmetric carbon, but it'll be represented as a tetrahedron. So once you see the wedge and the dash, you do want to go check and say, are there 4 different groups? So this molecule on the left, I see this carbon here is drawn tetrahedrally, and I see it's bonded to hydrogen, methyl, ethyl, and OH. So it's bonded to 4 different groups. First thing we're going to do is assign priority to those groups. Priority rules, remember, atomic number is our biggest differentiator. So of the 4 groups, which one of these would have highest priority? This is for anyone who's watching. Sorry? Well, anyone who's sitting in front of me watching. Sometimes people can be so sarcastic. Oxygen. Oxygen is the highest priority because oxygen has a higher atomic number than carbon or hydrogen. So priority 1 goes to oxygen. Then I have 2 that are bonded to carbon. They're still going to be relatively simple to assign priority to. How do I assign priority? All right, both of these are carbons. Then I have to look at what each one's bonded to. Carbon down here is bonded to another carbon and 2 hydrogens. Carbon down here is bonded to 3 hydrogens. So this one ends up as priority 2. The methyl group ends up as priority 3. And the hydrogen ends up as priority 4. So I've assigned priority. Number 4 is going into the page. I trace 1 to 2 to 3. That's counterclockwise with hydrogen going into the page. So Counterclockwise, hydrogen going into the page, that's going to be S. So the question is there some sort of mnemonic device to remember that? I don't have one, but you got, crowdsource it. I'm sure you can come up with one. So this molecule on the left has S configuration. All right, the molecule on the right, I'm going to go ahead and do the same thing. Here's my chiral center. Highest priority is going to be nitrogen. Notice, even though there's an oxygen on this other group, I go one atom at a time, and I'm comparing nitrogen to carbon to carbon to carbon. So nitrogen is going to be the highest priority group. Now I have 3 carbons to compare. The carbon out here on the right is bonded to oxygen, oxygen, and carbon. The carbon down here at the bottom is bonded to hydrogen, hydrogen, and hydrogen. And the carbon up here to the left is bonded to carbon, hydrogen, hydrogen. So, who gets priority 2? The one on the right. So this will be priority 2, priority 3, the one on the left, and then priority 4 is down here. So looks like I'm in the same boat here. 1 to 2 to 3. Counterclockwise, number 4 is going into the page. Again, this is S. Kind of poor planning on my part. I should have. So the question is, what about 4? 4 we leave out. So we're only tracing 1 to 2 to 3. And we make sure that 4 is either on the wedge or the dash. But then when we're tracing clockwise or counterclockwise, we're only looking at 1, 2, and 3. All right, so here is a molecule that I would like you to try applying the system to. There are 2 stereocenters. Assign R versus S configuration to the 2 stereocenters. All right, so this example actually has a curveball in it. So if you were trying to do it, you may have run into trouble with that curveball. Let's do the bottom stereocenter. I'm going to highlight that one in red. And let's assign the priority to the 4 groups around that. The lowest priority is pretty clearly going to be this methyl group, which is number 4. All right. So I have the methyl group as priority 4. Now I look at the other 3 things it's bonded to. It's bonded to carbon, carbon, carbon. So I've got to look at what each of those is bonded to. The one on the left over here is bonded to carbon, hydrogen, and hydrogen. The one on the right, also bonded to carbon, hydrogen, and hydrogen. The one at the top is bonded to oxygen, carbon, and carbon. So we have a clear winner for top priority. Top priority is going to be up here, number 1. For the other 2, it's still a tie. So what do we do in the case of a tie? Go to the next atom. All right. So I go to the next atom out, both carbons, and now I look at what they're bonded to. This one over here is bonded to, on the left, is bonded to carbon, hydrogen, and hydrogen. The one on the right is bonded to oxygen, oxygen, and carbon. So now we have a clear winner for priority 2. It'll be the one on the right. And then that means the one on the left is priority 3. So to assign R versus S to this one down here, I have 1 to 2 to 3 going clockwise. Number 4 is going into the page. So this stereocenter is going to have R configuration. The other stereo center there actually has a bit of a curveball, and that's because priority 4 turns out is not on a wedge or a dash. So I'm going to wait till next time to explain the other stereo center. We'll call it a day there.